Welcome back, folks. We are in section 10.2, and we're going to be talking about comparing two means. Let's get after it. Here's the situation. We have two different populations or treatments, treatment or population 1 and number 2. The parameter that describes those two populations are mu1 and mu2. Why? Because we're talking about means. The statistic that represents those two samples would be x bar 1, x bar 2, and then the sample sizes are n1 and n2 respectively. You're going to see a lot of parallels between what we did in this section, what we're going to do in this section, and what we did in 10.1, which was comparing two proportions. Also want to mention there are some parallel sections in other chapters, and they are 7.3, which is where we talked about sampling distributions for means. 8.3, where we talked about confidence intervals for means. And 9.3, where we talked about significance tests for means. Okay, in this section we're going to be comparing populations or treatments by doing inference about mu1 minus mu2. The statistic that we use to measure this is going to be x bar 1 minus x bar 2. And to use that for inference, we must know about the sampling distribution for x bar 1 minus x bar 2. So on this first page, we're going to spend our time talking about the sampling distribution of this statistic. And then, much like we did in 10.1, the first 2 pages are going to be mostly theory and background, and then we'll get into some examples. So let's talk about the sampling distribution of x bar 1 minus x bar 2. Let's say we choose an SRS of size n1 from population 1, and that population has a mean of mu1, and we take an independent SRS of size n2 from population 2 with mean mu2. The following is true about the shape, center, and spread of the sampling distribution of that statistic. First, when the population distributions are normal, the sampling distribution of this statistic is also normal. In other cases, the sampling distribution of x bar 1 minus x2 is approximately normal if sample sizes are large enough. That should look familiar. Center of this sampling distribution, the mean will be, the mean of x bar 1 minus x bar 2 will be mu1 minus mu2. And then spread here, the standard deviation of the sampling distribution of this statistic is this guy right here. A couple quick reminders here. Even though we are subtracting two statistics here, variance adds, and then we take the square root to get back to standard deviation. By the way, this formula is true as long as each sample is no more than 10% of the population if we are sampling without replacement. Now, the conditions that we've been using for inference match up with each of these ideas, and I hope this is of no surprise to you. This is the normal / large sample condition. And we will talk about small samples in a minute. The center of the distribution, well, in order for this to be true, we must have a random sample or random assignment of treatments. Last but not least, the spread of the sampling distribution. This formula is true with the 10% condition. And remember this, the 10% condition is for sampling without. Just a quick reminder here, if we are doing experimentation, we're often not sampling a population. We have volunteers, so the 10% condition does not apply. I want to talk a little bit now about standard deviation. I want you to recall that in practice, it's unrealistic to know the standard deviation of the population. So how do we account for this, and what problem does it present to us? This is what I recall. Okay, so we can substitute the sample standard deviations S1 and S2 for the population standard deviations sigma 1 and sigma 2. However, this will produce more variability than expected. And I want you to remember when we played class bingo. That was the example that illustrated this. So how do we account for that? Well, if this is unrealistic, and we use something that's more realistic, which is the standard error of x bar 1 minus x bar 2. So if that's more realistic and we use that, but it gives us more variability than is expected, how do we account for that? The answer is, you guessed it, folks, we'll need to use the t-distribution. All right, so let's go ahead and shut this page down, and then we'll pick up page 2 in a new video.